We are about to tinker with the remainder formula for the integral test. Before we get into the paperwork for that, I want to show you how you can ask for partial sums of our series fairly easily. The last week's computer exercises, I demonstrated Maple, and so this time I'll demonstrate Wolfram Alpha because not everybody is using Maple. You can do all of this stuff in either platform. In Wolfram Alpha, asking for a summation is relatively simple. Wolfram Alpha is good for understanding what you type in if you type it in a sensible way. So it will turn out that the first thing we're going to look at is a series of terms 1 over n cubed, and we're going to be asked what is the 10th partial sum. In other words, what do we get when we add up the first 10 terms in the series of 1 over n cubed? And so rather than doing a term-by-term calculation and addition, I'm just going to ask Wolfram Alpha to do a sum from, the underscore means, hey, this would go under the summation sign, right? A sum from n equals 1 to 10. So the n equals 1 would go below the summation, the 10 would go above, and the recipe is 1 over n cubed. And it's as simple as that. Wolfram Alpha will echo the result. Well, here is a really exact fractional version of that result, which is totally meaningless for us. And then here is the decimal approximation right there. And so when we get back to the paper version for this problem, that result will be in place. So we just saw in Wolfram Alpha that if we took the series 1 over n cubed, starting with n equals 1, and added up the first 10 terms, 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, and so on, we would get about 1.19753 as the result. Now, this is a convergent series, as you should know at this point, which means this overall series has a numerical value. We might want to know, if we've only added up the first 10 terms, how wrong can we be in terms of a comparison to the actual true value? In other words, what's a bound on the error after S10? To demonstrate convergence for this particular series, we might be tempted to use the integral test because the function 1 over x cubed can be easily integrated, and it also satisfies requirements that are necessary in order to use the integral test. I won't go through those here, but I recommend checking into those lab notes, those computer exercises notes, and the regular class notes to see what those are and confirm you know why we would be allowed to use the integral test for this particular series. Given that the integral test would work to determine convergence of this series, the integral test would also work to determine bounds on error, in other words, remainders. And the integral test is sort of nifty because the integral test tells us that the remainder after the first n terms, or the remainder after the nth partial sum, is no bigger than what you would get if you pretended that the series formula was a function of x and you just integrated from n on out to infinity. And so if we can calculate this integral, then we can calculate the remainder after 10 terms or after 100 terms or whatever it is. And this one's actually pretty simple. If you don't follow this immediately, feel free to step off to the side and do it. It is an improper integral, so it has to be done properly as an improper integral, but it ends up becoming 1 over 2n squared. And so that means that R10 is 1 over 2 times 10 squared, which turns out to be 0.005. So for this particular infinite series, which converges and has an actual value associated with it, if we only add up the first 10 terms in the series, we are no more than 0.005 away from this mysterious true value that we don't actually know. The follow-up question here is, okay, fine, after 10 terms we are 0.005 away. How many terms do we have to go out if we want to be no more than 0.001 away? Well, we already have the recipe for the remainder after n terms, so why don't we just see what value of n does it take to make the remainder less than 0.001. So doing reciprocals, And remember, if you do reciprocals on both sides of an inequality, you have to flip the ordering. I probably should have done the 1 over 0.001 first, but I was excited to divide by 2 and do the square root. So not the most efficient way to get this value, but if you punch those numbers, this turns out to be about 22.36. And again, there's a matter of interpretation here because we are calculating n. N is a counter of the number of terms, so we have to report an integer. The question is, how many terms do we need to use to get our error within this tolerance that we've specified? We cannot say that we need 22.36 terms. That doesn't make sense. What we've learned is that the value of n needs to be bigger than 22.36. The next eligible value of n, which is greater than 22.36, is 23 terms. And so in order to get our error less than 0.001, that means we would have to collect 23 terms.